All right, sound testing. Just making sure things are good. But I guess we're just gonna start. All right, we're gathered here to basically talk about stoichiometry for chemistry. This is like the introduction, like the bare start of stoichiometry. All right, let's get to it. So when we're talking stoichiometry for chemistry, we're just basically doing rates. So conversion rates starting from algebra 1. So for example, when you have like 1 hour, that is equivalent to 60 minutes, right? So when you want to figure out your timing between going from hours to minutes, then you need this conversion rate right here. So let's say, for instance, you have 2 hours. So starting from 2 hours, if you wish to figure out how many minutes you have in 2 hours, most people don't need this little conversion rate, but we're just gonna do it. So when you convert from hours to minutes, you must multiply 60 minutes on top, and then 1 hour on the bottom. Again, this is just the conversion rate. Because by definition, 1 hour is 60 minutes. And you notice the way I've oriented the fraction right here. Hours on the bottom, because we want the dimensions to cancel out. So if you perform the multiplication, what's going to end up happening is the hours will cancel with the hours. And then you're left with just 2 times 60, which is 120. And then the leftover units are minutes. So thus, there are 120 minutes in 2 hours. Pretty simple. Do you have to do this for converting time? Probably not. But the idea is conversion rates, okay? Alright, so that's simple enough. Getting into, I guess, No, we're still going to continue on the rates. So basically, when you're dealing with chemistry, a lot of what you'll be doing in chemistry is going to be very mechanical, especially early on, because most of the time you won't be learning very much about chemistry per se. It's just the operations, it's just the machineries that you need in order to do problems. This is at like the high school level or the like undergraduate level introductory courses for chemistry. Okay, so going back to conversion rates, with more time, of course, you can have more bizarre numbers. Like you have 1.2 hours, and then you wish to figure out how many minutes are in 1.2 hours. So all you need to do is multiply by the conversion rate. So again, by definition, it's going to be 60 minutes for every 1 hour that you have. So when you perform the operation, the hours will cancel out and you're left with 1.2 times 60, which is 70, what was it? 72.7.2, right? Wait, I can't do basic math. Okay. So the 60, you have the 0 and then the 6 times the 12, which is 72, and then you move the decimal over, so that's going to be 72 minutes. And then, of course, you notice something very important. The way I orientated the conversion rate, we didn't do it as in this particular fashion. It wasn't 1.2 hours times 1 hour over 60. So make note. And then the reason why we didn't do that is because you end up with complicated dimensions. You're going to end up with 1.2 times this fraction on top. The numerator is 1 hour, so when you multiply it, you get a very awkward 1.2 hours squared. and that is over 60 minutes. Now, technically, this is not wrong. It's just really bizarre, and there's no real reason you want to do this. You don't want hours squared. So again, when you are multiplying it, make sure you orientate the conversion rate correctly so that you can cancel the units. Because, you know, you want nice clean units in the end, most of the time. All right. That's the idea behind dimensions and multiplying dimensions. It's called dimensional analysis when you work with science. I guess the first major taste is when you do word problems for math, and then they start becoming more prevalent in chemistry. And then, but you also see them in physics, not so much in biology. But moving on. So for chemistry, you're going to be doing a lot of recipes, and all you need to do is figure out the ratios in your chemistry recipe. That's going to be, I don't know, some far-flung topic in the future. But for the most part, just know how to navigate a recipe, like baking. But we'll start off with a very easy recipe just to ground the situation. It's not going to be chemistry per se, but you will need it for chemistry, I guess. At least when you're first learning it. As you do more problems, it's going to become more naturalistic, and then you won't need to have such scaffolding. Okay. So let's talk about constructing a bike, because that's pretty easy. So when you're constructing a bicycle, we're going to say we're just assembling it. We ordered some parts from the factory, and it's like a really, really simple construction. So here's a recipe. You're going to have one bike frame. The bike with the ram horns. It's one of those road bikes, you know. Okay, so that's going to be the frame, and then of course you're going to have to put the wheels on it. So again, we're just going to simplify a kind of a complicated situation. So it's going to be, the recipe will read, if you have a bike frame, then all you need to do is add wheels to this bike frame. And then what you're going to get is you're going to get one bike, right? Kind of lazy, let's just put bike. Right? And that will be wrong, because this is not the right ratio. So if you have one frame, unless it's a weird unicycle, you actually need a second wheel for that one. So let's do that. What's my selector? Hold on. I can't believe it. I've been using this drawing program for like 10 years, and I forgot how to... Wait, what? Hold up. Technical difficulties. Why is it so bizarre? I guess that's the streamer brain, right? Things you know how to do before. Oh, here it is. Okay. Hi. Well. Okay. So we have a ratio. For every singular frame that you use, you must put on 2 wheels in order to generate a bike, a full bike. So those are the wheels. So we have here a kind of a ratio between parts. So we have a one bike frame. I'm going to color code this so it's more visually informative. So we have one frame. So if you have one frame, it's going to require... Where's my color? Hold on. This really is streamer brain. Huh. Okay, well, let's keep it simple. Well, there it is. So if you have one bike frame, then you need 2 wheels. We'll put the 2 greens for the wheels, and then the 1 red for the 1 frame. So that's going to be your recipe. And you can generate 1 bike if you assemble it correctly, right? So there are multiple ratios you can set up from this recipe that we have for bikes. So here are the recipes, right? Here are the ratios, I mean. So if you have one frame, then all you need to do is, if you have, I'm sorry, if you have one frame, you can use that to make one bike, assuming you have enough wheels. If you have one frame, as long as you have, for every 2 wheels that you have, you can also assemble one bike. And of course, there's even more ratios you could set up. So if you have 2 wheels, you can theoretically make one bike. So you guys see how this is a ratio. This is one ratio, this is another ratio, this is another ratios. So if you love ratios, here they are. But there are, I think, 3 others, because the orientation is also important. So what you can do is you can also say that there are going to be 2 wheels for every single one bike that you have. So ratios. Alright, but we're going to be proceeding from left to right fashion. So if you have the ingredients, we're going to make the product, which is the bike. But just be aware that you can go forwards from left to right, and you go backwards from right to left. And we're just going to go through multiple instances. Alright. So let's start off with a simple problem, of course. Let me select the color. I only have blue, green, red. Oh my goodness. Hold on, there's gotta be a way to get my color. Again, I've been using this program for like 10 years. Oh, here it is. Oh, okay, I found it. What do you know? Alright, so let's go to some brown color. Alright, so here is a problem. So if I gave you 2 frames, and I give you 4 wheels, the question is, how many bikes can you assemble, assuming all the parts connect? Well, since you have 2 frames, it's going to be 1 frame will need 2 wheels, right? And so it's a 1 to 2 ratio. Let's use some color. So for every 1 frame that you have, you require 2 wheels. So if we're assembling the bikes, let's start with the 2. We have 2 frames. Well, let me put the spacing a little better. Okay, so 2 frames, right? So given that you have 2 frames, how many wheels will you need to use those 2 frames? So what you need to do is you need to multiply by the conversion rate factors. So here's the conversion rate straight from the bike recipe right here. So again, for every 1 frame that you have, you're just going to require 2 wheels. Well, that's a pretty ugly green. Fully saturated. Okay, so 2 frames, we're multiplying it by the ratio, by the rate. It's going to be 2 wheels for every 1 frame. You will see that the frames units cancel out as per dimensional analysis. So that's nice. And then you have a leftover 2 times 2, which is 4. Perfect. Easy algebra, right? Or even pre-algebra. So 4 wheels. So what does this mean for us? It means that you will require 4 wheels to use up all the given frames right there. Do we have enough wheels? Yes, we do. It's 4. See that? 4. So because we have 4 wheels, we can therefore use all the frames and we will make enough bikes. The question is, how many bikes will we make? Without doing very much math, you can just say, oh, you could already see it. If you have 2 wheels and you could use up all of them, if you have 2 frames and you could use all of them, since we have enough wheels, then you can make 2 bikes. So not much math is needed, right? But, since we're starting off, let's just do the full motions as a form of scaffolding. Just get used to the motions, right? Okay. So again, we already know we have 2 frames. That's the given amount. I put it in this maroon, I think it's maroon color. And then all you need to do is convert using the conversion rate from the recipe. So for every one frame that we use up, we can generate exactly one bike. So populate this little chart. You notice that I switched it. I'm now putting this little table tabular looking thing instead of having the fractions. It means the same thing. So this is like the numerator, and then this is like the denominator. It's essentially just a fraction. Why do we have this distinguishment? Because, I don't know, it's neater? Maybe? I don't know, I think it's neater. So from now on, we're not going to be multiplying by the fractions in the old school way from back in your math days. So when you multiply, it's going to be like, this is your initial quantity, and then you multiply by a fraction, right? So numerator to numerator, but we're just representing it in this table form. Because again, I think it looks neater, and it seems to be the convention that the majority of chemistry people adopt. So that's that. Okay. Back to the task at hand. Again, we have 2 frames. This is your given amount. And the recipe for assembling the bikes is going to be for every one frame that you use. I'm going to abbreviate it as FR. So for every one frame that you use, you're going to make exactly one. You can assemble one bike. You know what? I'm going to use singular letters. Okay, there you go. So for every one frame that you use, you can assemble one bike according to the recipe. This is the conversion rate, straight from the recipe. This is the question that I've given. If you have 2 frames, all we need to do is just do the math. So we know that the frames units cancels with the frames. So 2 multiply just straight across, numerator to numerator, so you get 2. You're going to get 2. And then the leftover units will be B, and then the bottom denominator units, there are no units, it's just 1. This looks kind of ugly, so just beautify it. So 2 bikes. Very easy. Nice, right? 2, easy. There we go. Alright. I'm not used to not having anyone respond. I'm just talking to the vast void of space, right? Space void of the internet. Okay. So easy problem. But, we'll gradually ramp it up. For the future VOD users, if they will ever exist, you can just skip. There'll be hopefully timestamps. We'll see. Alright, so let's suppose we have different numbers now. Suppose you have 10 frames and you only have 2 wheels. Let's put 10F and then 2 Ws, right? So the question is, how many bikes can you assemble if you have 10 frames and 2 wheels? So for the most part, you could kind of see the answer already. If you only have 2 wheels and you have a lot of frames, then you could only make 1 bike, right? So you can see that. But again, we're just going to go through the motions. Alright, so you're going to pick the one you want to generate answers. So given that you have 10 frames, and given that you have 2 wheels, the question is, how many bikes can you farm? Okay. So there are 2 strats. You can work with the frames or you can work with the wheels. It's going to be the better strategy to work with the wheels, which for future explanations, it has to do with something called limiting reactants, but don't worry about that at the moment. So let's just arbitrarily select 10 frames since we're reading from left to right. So if you start off with 10 frames, that's our given amount. The question is, how many bikes can we theoretically build? This is not the best question to ask first, but more on that later. We're going to still go off that question. So if you have 10 frames, how many bikes can we theoretically construct? So back to the recipe. For every 1 frame that you use, you would generate 1 bike. So cancel units. Just multiply straight across. Multiply straight across. Canceling units as you go to keep things simple. So frames, units cancels with frame units. And then you're left with just 10B. So in other words, if you have 10 frames, if you can somehow use up all of them, then you can assemble 10 bikes. But can we use up all 10 frames? And the answer is no, because you don't have enough wheels. How do we know we don't have enough wheels? Without doing any math, you're like, wait, you obviously only have 2 wheels. How can you put them on more than 1 bike? And that's correct. But let's be more mathematically robust, right? Because you got to show your work for the teacher probably, or show for the professor. Well, probably not the professor, but like the TA or something, right? Or someone, I mean. Okay, so let's show the work. How do we know that 10 frames is not enough to make 10 bikes given this specific situation? Well, obviously, again, it's the wheels that's stopping us, but let's see why. So given that you have 10 frames, how many wheels will you need to use up all 10 frames? We're going to go to the recipe. It's going to be for every one frame that you use, you require 2 wheels right there. Again, this is straight from the recipe. So once you do the mathematics, simple, cancel units, just multiply straight across. So what do we get? We get 20 wheels. What does that mean? It means that in order to use up all 10 frames that you were given, you require 20 wheels. Do we have 20 wheels? No, we don't. Since we don't have 20 wheels, we know that this one is stopping us from assembling more bikes. So what do we call this one? You can call this one the limiting reactant. It's called the LR. So no, it's not a very fancy term, but just understand that it's stopping us from making more bikes. So to figure out how many bikes we can assemble, you're not going to use this number because we already saw that it gives us the wrong. We already saw that we don't have enough wheels mathematically right here. So rather than framing our answers, framing the question, framing the work by using the frames, we're going to use the wheels instead. Okay? So don't use this number because it's something called excess. There's an excessive amount of frames. So theoretically, if you have an infinite number of frames and you only have 2 wheels, there's no way you can make infinite bikes. Okay? There's no weird exchange going on. You can't change the frames. You can't go to the store and say you want to trade the frames in for some wheels. So we're just as is. If you have 1 million frames or an infinite amount of frames, it doesn't matter because if you only have 2 wheels, you can only make 1 bike. So excess is going to be ignored for now. Later on, you'll see that for future problems, they will come back, but don't worry about it for now. So 2 wheels, that's going to be our given amount to work with. So given that you have 2 wheels, how many bikes can you assemble? It's going to be for every one of, I'm sorry, not 1 anymore. Why is the 1 not on the bottom here? Because that's for the frame. So the 1 goes up in the numerator right there. So for every 1 frame that you use, it's going to require 2 wheels. Okay, so that's 1 fraction that we can set up. So if you cancel units and you get the answer here, that basically tells us how many frames we need. And yes, we do have enough frames because we have 10. But that's not what we're trying to answer, right? So the question is, how many bikes can you assemble given that you have 1 wheel? So don't frame the setup using frames. You want to use bikes. You want to use a conversion rate going from wheels to bikes. So if we use up, according to the recipe, if you use up 2 wheels, you will generate 1 bike. So 1 bike right there. So doing the mathematics, very simple mathematics, multiply straight across, easy. So we get 2 times 1, and we have b. So what is, I'm sorry, make sure you cancel before. So divide the numerator by 2, divide the denominator by 2. So 1 bike. So what does that mean? It means that you can only make 1 bike given that you have the 2 wheels and 10 excessive amount of frames. And that's the answer. Nice. Very easy. I've been saying that for the past, what, how many minutes? But it truly is. It truly is. Okay. But let's make things a little more annoying, right? Because these are very nice numbers. Let's make some disgusting numbers. Kind of. So how many frames do we have? We have 13 frames. How many wheels do we have? We have 18 wheels. So given that you have this scenario, how many bikes can you construct? So now we'll formalize things, you know, by actually typing things up. All right, given, I can't even see my typing. Hold on, I'm just gonna read. It'll show up in a moment. So given that you have, or rather, given that there are 13 frames and what was it, 18? Yeah, 18. Given that you have 13 frames and 18 wheels, how many bikes can you assemble? We're going to use the passive voice. How many bikes can be assembled? For reasons, right? Wait, where did it go? Oh my goodness. Okay. Like I said, I totally... Oh my goodness. Hold on, let me test. Quick test. Okay. Well, that's kind of awkward. I typically don't type in this drawing program, so I guess. Well, now I know. Okay, I'm just going to write it. Unfortunately, for all text, you will have to appreciate my writing. Unfortunately. Maybe if I go on MS Paint sometime in the future. But for now, we're sticking with this. Okay, so given that you have 13 frames and 18 wheels, how many bikes can you construct? So from experience, you may be able to already see that there aren't going to be enough wheels to use up all the frames, because you know the recipe is for every one of these you need 2 of those. So in order to use up all 13 frames, you times 2, which is going to be 26 wheels. We don't have 26. Okay, but showing our work, formalizing the work. So if you have 13 frames, how many wheels will be required? Since we're talking about frames and wheels requirements, then we use the red and green ratios. So the ratio is for every 2 wheels, 1 frame. So do the work, cancel this with that, and you will see that you have 26. You will need 26 wheels. Do we have 26 wheels? No, we don't. So thus we can say this is the living reactant or living region, whatever you want to call it. There's a difference between those two when you say something is a reagent versus just a reactant, but don't worry about it for now. So this one is excess, so we're gonna ignore it for now. All right. So this we did this work just so that we can do more work, the right work, I should say. Let me write excess. All right. So we know that these are going to be the limiting reactants. So we're going to base our problem around wheels, and we're going to use the ratio between wheels and bikes to figure out how many bikes we can construct. We don't need this number anymore for this problem. All right. So given that we have 18 wheels, according to the recipe, it's going to be 2 wheels for every 1 bike. Cancel, cancel. So we can generate 18 bikes. I forgot to divide by 2 again. Oh my goodness. Divide by 2. Divide by 2. Always simplify before you multiply. So 9 bikes. So that's it. That's the answer. You can generate 9 bikes. Okay? All right. As I review this in the VOD, it's going to be such a scuffed review. But we can't get enough of that scuff, right? Let me make a new layer. All right. Now, let's make things closer to the reality of chemistry, right? So once, yeah, you know what? No. Let us just do more practice. So again, if you already know this stuff, just skip on. If you're one of those VOD people, if you're one of the live people, you don't exist. All right. So let's just plant a bunch of numbers. I'm just going to randomize, quote unquote randomize. So we have 13, we have 7. This is problem 1. We'll call this one problem 1A. And then, wait, that looks weird. Okay, so that's problem A is 13, 7. And then problem B is going to be 21. And then problem C is going to be, let's make things interesting. If you constructed 20 bikes and then you had 100 wheels, how many frames must you have had? So be aware that as a problem maker, a problem maker can make a variety of problems going forwards as well as going backwards. So be comfortable going both ways. All right. We'll put one more for good measure. So if you had 30 frames and then you made 20 bikes, what's the minimum amount of wheels that you need in that situation? All right. Problem 1. Problem 1A. So we have 13 frames, we have 7 wheels. We can already see that the wheels are going to be insufficient for using up all the frames, because again, if you use a ratio real quick, just do a real quick analysis. For every one frame that's 2 wheels, you need 26 wheels, but you only have 7 wheels. So ignore this number for now. So the question is, how many bikes can we construct? Well, we have 7 right here. The ratio between bikes and wheels used is going to be 2 to 1. So therefore, you can only make 3.5 bikes, whatever the hell half a bike means, right? So for our purposes, when we're counting objects, we don't have half objects, right? So for this one, we're just gonna leave it as 3.5. We will accept the half bike for certain reasons, okay? Don't worry about it. So trust in the process, trust in the ratios, trust in the recipes. We can make 3.5 bikes for problem 1A. So that's done. And then problem 1B, as you look at that, you have 20 frames, you have only 1 wheel. Clearly, there's going to be, you know what, let me switch the number. I'm sorry. I don't like this. Sometimes when you don't like something, just got to change it. All right, so there we go. So if you have 1 frame and then you have 20 wheels, the question is, how many bikes can you generate? You can already see it. Again, not much work to do. If you have 1 frame, doesn't matter how many wheels you have. You can only make 1 bike. But again, showing the work. So for 1 frame, for every 1 frame that you use, you can generate exactly 1 bike. 20 wheels are excess amount. So the frames are the limiting reactants, so LR for that. So when you do the mathematics, you can only get 1 bike. Very boring. We can do with all those wheels. So only 1 bike. Okay. That takes care of 1B. Moving on to 1C, we have question mark. We don't know how many frames we have, but we know that we have 100 wheels, and we know that we've generated 1 bike. Since this is a lot of wheels, you can kind of feel that if you made 20 bikes, you must have had at least 20 frames. That's a kind of a feely for the problem, right? But again, just trying to be as mathematically robust as possible. We're going to start backwards. We're going to start with our given amount right here. So if you have 20 bikes, theoretically, it's going to be hard to show the work. Let me think. Oh, yeah. Like, I forgot how to use my drawing program again. 10 years of my drawing program. No, even more than 10 years. I've been using this drawing program for like 12 years. It's so crude. Anyway. We have 20 bikes that we've assembled. So 20B, that's going to be our given amount, right? We have 20 bikes, so we're going to follow the recipe. If you have 20 bikes, how many frames must you have used? Again, showing the work. So we have 1 frame in the numerator, and it's going to be, what color did I use? Oh, blue. Oh my goodness. So the frame is red, the bike is blue. Yeah. So for every 1 frame, you can generate 1 bike. So again, make notice that this ratio, which we usually do it the other way, has been flipped. because you want the bike units to cancel. So bike units cancels with bike units as per dimensional analysis. You perform the simple operation 20F. There are no numbers to cancel, so you just have 20F. So there must have been at least 20 frames right there. 20 frames. And that's it. How come we didn't use the 100 for 1C, right? It goes back to the limiting reacting. We already, from the intuitive, I guess from the quick inspection, we could kind of see that 100 is kind of a lot. It could be 1,000 wheels. It doesn't matter. If you've only made 20 bikes, you must have had only 20 frames because limiting reactants, right? Or rather, this is the limiting product. If you compare the numbers, right? If we could have used up all these wheels, then we would have generated a lot more bikes. I hope that's sufficient as an explanation. All right, anyway, moving to the last one. So for the last problem, we have 30 frames, and then we have question mark amount of wheels, and we have 20 bikes. Okay, that's actually impossible. We can't make... No, I'm sorry. No, that is possible. Okay, almost goofed. Okay, so given that you have 30 frames, how many wheels must you have used in order to make 20 bikes? Going back, we're going to assume, well, no assumption. If we were able to use up all these frames, then we would have had 30 bikes. But we don't have 30 bikes. We only have 20 bikes. So that tells us that this was the limiting reactant. Or the limiting product, or whatever you want to call it. Actually, I shouldn't confuse things. Product is on the right side. Reactants are on the left side, by convention. Okay. Let's go backwards. So we have 20 bikes. Fully assembled bikes. And then the relationship between wheels and bikes. So for every 2 wheels that were used, must have generated, what color was it? Oh my goodness. Okay, blue. 1 bike. So for every 1 bike that is assembled, there must have been 2 wheels that were used. And this is the recipe rate from recipe. Okay, do the math. That's the setup. So 20 times, just multiply straight across. So 20 times 2 is 40. Bikes units cancel. Easy. There must have been 40 wheels, and that's going to be it for D. So there it is, 40. 40 wheels. Alright, that basically takes care of those ones from 1A to 1D. Right? Okay, but again, that's still kind of a little bit away removed from actual chemistry mechanics, but we're getting there, promise. Alright, so how to make it closer to chemistry? Well, instead of giving you the number of frames and the number of wheels, what I'm going to do is I'm just going to be a little extra, right? I'm going to say, you know what? Instead of telling you how many actual frames you have, I'm going to say that you have 100 pounds worth of bike frames. And then, so you could already, I'm using pounds, so you can kind of figure out, or not figure out, you have an idea of where I'm at, but whatever, right? So if you have 100 pounds worth of bike frames, and I'm going to give you 100 pounds worth of, I'm going to give you 200 pounds worth of wheels, right? So the question becomes, how many bikes can you thus assemble given those constraints, given those amount of reactants? So mathematically, it just, without thinking too much about it, someone might be tempted to say, oh, you know what, this is 100 pounds of bikes, this is 200 pounds of wheels, so therefore, can't you just make 100 pounds of worth of bikes? And by the way I'm framing the question, you could already tell that that's absurd. That's definitely wrong. Because number one, the bike frames themselves are already 100 pounds. Shouldn't they weigh more now that you're attaching wheels to them? And yes, that is the answer. But there's more to it than that, of course. There are other reasons why this answer is absurd, because you are working with weights amounts. You're not working with actual parts, if that makes any sense. Because if I tell you that you have 100 pounds worth of frames, you have no idea how many frames you actually have. What does it mean to have 100 pounds of frames? Does that mean you have 50 bikes? Does it mean you have 2 bikes? What does it mean? And it doesn't, quite frankly, it doesn't mean anything. So I need to tell you, I need to give you some sort of conversion key. Because what kind of bike frames are you dealing with? Are you dealing with carbon fiber, which tends to be lighter? Are you dealing with steel bikes, which tend to be heavier, right? Like, which kind of bikes? So I'm going to tell you right now explicitly, for every, you're working with 20-pound bike frames. I forgot if that's heavy. I think that's heavy. I think 18 is like a pretty good pound for a bike frame. I don't know. I'm not a real biker anyway. So we have 20 pounds. For every 20 pounds, that's essentially going to be 1 frame. Again, this is like maybe an aluminum bike or something. So for 1 frame, if you weighed that on a scale, on a good scale, it's going to be 20 pounds. So now you could actually figure out how many frames you actually have. So back to conversion rates. This one is, all we need to do is multiply the conversion rate to the pounds. But of course, this is orientated in the wrong fashion. So here's the setup. Given that you have 100 pounds worth of bikes, how many frames do you actually have? So this one is going to go denominator. And that was numerator. Make sure you orientate it correctly, otherwise you get pounds squared, which, what the heck does that even mean? Now here we go. Alright, so there's the setup. You will see that the pounds units now cancels out with the pounds units. You always simplify before you multiply. So if you divide the bottom by 20, you can divide the top also by 20, which will leave 5. Just multiply straight across. Technically a 1, but let's leave it out. So what does this mean? This means that given that you have 100 pounds worth of frames, you only have 5 frames. You don't have 100 frames, unfortunately. Okay, so that's part 1. That's a lot of math. There it is. But, you know, you're going to have to do it for the wheels here as well. So the question is, how many wheels do you actually have? And at the moment, you don't know, because I haven't told you how much each individual wheel weighs so that you can figure out how many actual wheel pieces you have. So here it is. I think wheels are 2 pounds. I don't know. Don't ask me. I just make things up, okay? So for every 2 pounds, that seems kind of heavy. Maybe it's one of those thick tires, those super thick tires. Yeah, it's going to be a thick tire, okay? Maybe. I don't know. So for every 1 wheel that you have, it's going to be 2 pounds. That's your conversion rate. Now you can use this to figure out actually how many wheels you have. And this time I orientated it in the right fashion because the pounds are on the bottom. So given that you have 200 pounds, how many wheels do you got? So cancel your units. Pounds cancel with pounds. As per dimensional analysis, divide top by 2. Divide bottom by 2. Multiply straight across. 100 wheels. So we already know that that's way excessive amount of wheels. But, you know, show your work. Here it is. Later on, you will be able to skip your work. But for now, since this is just the beginning, make sure you show all your work. As you progress and build experience, you will know which ones to leave out, unless your teacher is very strict. So we have 100 frames, we have 100 wheels. The question is how many bike frames? Again, you can maybe already see it. If you have 5 frames, you can make 5 bikes. Excessive amount of wheels. But showing the work. Okay, in order to use up all 5, so arbitrarily selecting this for analysis, if you have 5 wheels, if you have 5 frames, how many wheels will you require to use up all 5 frames? Here are the numbers again. 2 frames, 2 wheels. Keep putting the wrong stuff. 2 frames for every 2 wheels for every 1 frame. Cancel, cancel. And then you will see you will need 10 wheels. Do we have 10 wheels? We have more than enough wheels, so let's call this excess. So based off of this bicycle reaction, we can generate how many bikes. Make sure you show your work. So we have this is, remember, this work right here just tells us how many wheels we need. We're doing this as a precursor for the main setup, which is going to involve the limiting reactant ratio to bikes. So these are the numbers we actually are more concerned with. The 1 to 2 is just showing us which one will run out first, if you need to do it. Alright. So now that we know that the frames are the limiting, we'll bust out the 5 frames. There it is. Who cares about this? So for every 1 frame, 1 bike. As we progress, I'll be using less and less words as I'm doing the process. Cancel, cancel. 5 bikes. That's what we already said. So we can make 5 bikes. And the answer is done. But wait a minute. Aren't the units different now? This is wrong. Remember, this is wrong. So we start off with pounds. We were talking about things in terms of pounds. This is now in terms of quantity, number of bikes, not pounds worth of bikes, which might feel bizarre. So we're actually going to convert this to pounds of bikes. Why are we doing this? Because it's analogous in chemistry. Just trust me, okay? So the question is, how much does each bike weigh if we have 1 bike? You could kind of get it from the parts we already have. I already said that for every 20 pounds, you have 1 frame. That's rate number 1, and then we have rate number 2. For every 2 pounds of wheel, you have 1 wheel. So it goes following this recipe. If you just add 20 pounds, which is 1 frame, and then you add it up to 2 pounds per wheel, since it's per wheel, times 2. So what is the total weight of this bike? It's going to be 24 pounds, which actually sounds very heavy. Wait, I put BS. Why did... Oh, no, that's pounds. I'm sorry. Yeah, that's pounds. So each bike is going to be 24 pounds. Yikes. That's good for training, I guess. So 1 bike. 1 bike is our rate. For every 1 bike fully assembled, you have 24 pounds. Since we have 5 bikes, let's run it through this rate. So for every 5 bikes, that's our answer so far. So for every 1 bike you have, that's going to be 24 pounds. Yikes. Cancel, cancel. So how many total pounds worth of bikes do you have? 120 pounds. Wow. There it is. Again, there's no real reason for this problem to talk about it in terms of pounds of bikes, but it's just an exercise. Water check. Hydration check, yes. Okay. Wait, did I need that? No. Okay. So here are the magic numbers for every, again, 1 frame that you have. It's basically 20 pounds. That's really high. And then for every 1 wheel, it's going to be 2 pounds. And then from our derivation, once we assemble the bikes, we put 2 and 2 together, so to speak. So for every 1 bike you have, that's going to be a whopping 24 pounds. Again, it's probably good for training. You know, like when, for those anime protagonists, when they have the weights on them, they're like minimized or something, and then when they take them off, they're really strong. I guess it's the same idea. If you have 24-pound bikes, you too can be really powerful. But we need these numbers. This one is derived. This one was the ones that were the ones that I gave. Okay, so let's do an actual problem again. For how many frames do you have? We got, how many we got? 200 pounds worth of frames. And we're gonna have 50 pounds worth of wheels. So I'm not going to ask for pounds of bikes. Let's just ask how many bikes can we assemble. So remember to distinguish between weights and actual counting amounts. So how many frames do we actually have? So if you have 20 pounds worth of frames, just run the numbers, conversion rates. So 20 pounds for every one frame. Cancel that with that, you have 10 on the top. So that means you only have 10 frames. How many wheels do we have? So we have 50 pounds worth of wheels. That's our given amount, and this is again the conversion rate. So for every 2 pounds worth of wheels, 1 wheel. So cancel, cancel, 25. 25 wheels, very awkward. So the numbers, we have 10 frames, 25 wheels. You can kind of see this is already limiting, but let's show the work. Starting arbitrarily with our number of frames, since we know we now have 10 frames, how many wheels will we require to use up all 10 frames? It's going to be 2 for every one. Cancel, cancel. That means that we require 20 wheels. Do we have 20 wheels? Well, what did we just do compared to that one? So if you have 50 pounds worth of wheels, that means that you have 25 wheels. Since we require only 20 wheels, then we know that this 25 wheels is in excess. So that's nice. Now that we know that, let's work with our wheels. I'm sorry, with our frames, because we know the frames are limiting, so we'll just put LR. The nice thing about putting LR is that you're not committing yourself to saying it's reagents or reactants. You're just saying, you're leaving it ambiguously R, so it's an LR. So let's memorize that number real quick. We have 10 frames. Let's clear 10 frames. So now that we know the 10 frames are limiting, let's figure out how many bikes we can assemble. That's pretty nice. One bike, 1 frame. Cancel, cancel. How many bikes? 10 bikes. That's it. How many pounds of bike? I know I said we wouldn't answer it like this, but how many pounds worth of bikes that is? That's 24 times 10, which is easy numbers. Just add the 0. 240 pounds worth of bikes. Nice. Final answer. Yes. We're kind of ignoring sig figs, but that's okay. Since there's no uncertainty, we know that the actual counts of bikes is correct. Then you don't need to worry about. Actually, there's some uncertainty, but in a perfect world, each bike is exactly 24 pounds. We will say. Okay. No, that's not a perfect world. That's a terrible world if all your bikes are super heavy. I changed my mind. Okay. So that's it for that one. Again, that's just to illustrate the types of problems you'll be doing, the fundamental idea behind it. If you have weight type stuff, you cannot use your recipe. This is a... Let me get to the right layer first. This is your recipe. When you're using your recipes, you don't put your weights into your recipes. You have to use the raw count for your bike recipe. Pretty much. Alright, moving on. Let's actually do some chemistry, some legit chemistry problems. Finally. It only took us... How long was that? Over 30 minutes? Again, for all you future people out there, all 10 of you, maybe that's too optimistic, for all 3 of you, we're starting chemistry now, I guess. Okay. So here's a very simple reaction in terms of the balancing. So I'm just going to give the recipe. So here is your water making recipe. So for hydrogen, all you need to do is fix the oxygens, That's going to be pretty much one unidirectional, and then you go generate H2O. Nice. Water. Dihydrogen monoxide. And then we're good to go, right? And we're not good to go because, unfortunately, this is something called an unbalanced equation, which don't worry about it for now. We will likely do more of that in the future. But just understand that the assemblage is wrong. It's like saying if you have one frame, all you need to do is add one wheel and you can generate exactly one bike. That's wrong. Because you need two wheels to work with that one frame. And analogous to that one, you only have two oxygens here. You have two oxygens there, but you only have two hydrogens right there. So if you take this, this is analogous to the bike frame. So if you have one frame, you need to attach two wheels, right? So the I guess we're going into a little bit about, what do we call this topic? Just building the atoms. Lewis? No, not Lewis. No, this is still stoichiometry. Okay, so this hydrogen, a quick lesson on this notation. If you don't know it already, this is the element. These are how many elements are affixed to each other, covalently bonded to each other. This means that you have one hydrogen atom, and then you have two hydrogen atoms, and they are chemically bonded together, which makes H subscript 2. Which is kind of important to distinguish between other notations. So if you have two, H right there, that means that you have two separate hydrogens. Like there's hydrogen number 1, and then here's hydrogen number 2. They are not linked together. And then of course, if you combine those notations, if you have coefficient 2, and then you have subscript 2, that means that you have hydrogen number 1 connected to hydrogen number 2, and then you have hydrogen number 3 connected to hydrogen number 4. So there are two floating hydrogens. It's kind of confusing because when you learn about the vernacular, when you say oxygen, we typically refer to something like oxygen gas, which is diatomic, which is 2. It's not one oxygen, even though people say it's oxygen. So that's a subtlety that you will have to acquire later on, but don't worry about it for now. Okay, so going back to this one, why do we need to adjust the numbers? Because the pieces aren't sufficient in certain ways. So again, this one means that you have hydrogen number 1 linked hydrogen number 2. This one means that you have oxygen 1 linked to oxygen 2. So if you just magically cut this, surgically cut this, and then you take wheel number 1, stick it on, and then you take wheel number 2, stick it on, this is one complete assemblage for the water bike. But you have this randomly floating oxygen, which is, you can't have that. What's the reason? Don't worry about it. But just understand that not all the pieces have been used. Okay, and then according to one of the fundamental rules that you will learn in the beginning for chemistry, you can't destroy matter. It has to go somewhere. So this one, for our intents and purposes, we need it to react with some more hydrogens. So thus, you need another pair of hydrogens stuck together. So another H2 in order to split them up and stick on wheel number 1 and then wheel number 2. So that's a full assemblage. Adjusting the numbers, how does that going to look? We need one hydrogen and one hydrogen, so that requires 2 hydrogens. Let's use red for that. So 2 hydrogens, and then for the oxygen, which is O2, again it's diatomic, you only need 1. I have a feeling I'm flipping these colors. That's okay. So for every 2 hydrogens you use, 2 diatomic hydrogens that you will require 1 diatomic oxygen. And that would generate exactly 1 water. Let's use blue for water. That seems more intuitive. And then for oxygen, I think it's typically red for most visuals. And then hydrogen, I don't know what color. Let's just put it as green for now. Okay, so there it is. Now that's our recipe. For every 2 diatomic hydrogens, you need to react it with 1 diatomic oxygen, and that will yield 1 water molecule. Just like the bike, right? 2 to 1 to 2. All right. Oh no, hold up. Oh, there it is. I wish I didn't draw on the same layer. Drawing problems. Okay, there we go. Let's jump onto the other layer so that I don't erase these things. Alright, so here is the question. If you have exactly 4... let me use a different color. If you have exactly 4 diatomic hydrogens and then you have exactly 2 diatomic oxygens, the question is how many water molecules can you make? Just follow the recipe, which is based on actual amounts of stuff. If you arbitrarily take this number first, right? We have 4 hydrogens. So I'm just going to put 4H. What's the recipe? Let's figure out if we have enough oxygen. So for every 2 hydrogens that you use up, you will require 1 oxygen diatomic. So let's put the subscript actually, yeah. Subscript 2, and then subscript 2. Just to keep things in right notation, I guess. So hydrogens cancel out with hydrogen diatomics. Divide by 2, divide by 2. Multiply straight across. You have 2. You require 2 oxygen diatomics. Do we have enough? Compare it to what you actually have. Yes, we do. We have exactly enough. So since we have exactly enough, now we can proceed with the main bulk of the problem. We have 4 hydrogen diatomics. According to the recipe, for every 2 that you use, you would generate exactly 1 water molecule. So do the math. Cancel, cancel. Straight across. 2 water molecules. That's it. We are done with that simple count problem. So you can see that it's fundamentally the same as the bicycle assemblage problem, and you can bet that there are going to be annoyances like we don't give you the actual number of pieces of water, of hydrogens or oxygens. Instead, you're going to have something akin to weighted amounts, right? But before we go there, let's talk about something called moles first, because ain't nobody working with 1 or 4 molecules. That just doesn't happen because number 1, they're too small. Number 2, we don't have the tools to handle them on an individual basis like that. At least to my knowledge, I don't think we do. In the future, maybe. But understand that nobody works with 1 diatomic hydrogen and then they're gonna like stick it onto like 1 oxygen. That's just not possible, given our tools at the moment. So what do we work with? We actually work with something called moles. I don't know. I think it's an abbreviation, but put it shortly, moles. Let's say spell it moles. Moles are. Well, okay, the unit that's called moles is used as a grouping number, and it's basically a lot of atoms or whatever things you're counting. So if you want to think about if moles still feels kind of foreign, just understand that it's similar to the word dozen. It's a grouping type word. Dozen is a grouping type word. It's akin to couple or pair. It's akin to an oct. Wait, nobody says oct. What else are grouping? Oh, okay, those are the most common grouping numbers. Okay. So when someone says that they have a dozen of something, that just simply means that they have 12 of something. What is that something? Whatever context you're dealing with. If you have a couple or a pair, which is probably the most common group type words, you have 2. So if you have a couple of shoes, then you technically have only 1 and 1. You have a 1 left and you have a 1 right. So that's a couple of shoes, right? So if you have 2 couples of shoes, actually no one really says that. If you have 2 pairs of shoes, yeah, there you go. So if you have a single pair of shoes, then you have exactly 2 shoes. If you have 2 pairs of shoes, that means that you have 2 twos of shoes, which means you have 4. If you have a dozen pairs of shoes, that means that you have 12 times 2. That means you have 24 shoes. You have 12 lefts, and then you have 12 rights, right? But what does it mean for moles? Moles is very specific. It is a specific number. Is going to be 6.022, depending on which one you're referencing. 6.022 times 10 to the power of, and since I haven't done chemistry in a while, was it 23? Let me look this up real quick. I'm a fake chemistry teacher. It's called, to look it up, it's called Avogadro's number. It is 6.02214 etc. times 10 to the power of, okay, I'm correct. It is 23. Yes. So what does that mean? It means that if you have 1 mole of something, whatever you're looking at, if you have 1 mole of it, you have that many of them, which is a lot. And given the size of atoms, yeah, that seems pretty reasonable. So for the most part, when you are working with these type of problems, you're going to see numbers. In the beginning, you're going to see numbers like 4, for example, 4 moles worth of diatomic hydrogen. Okay, you have 4 moles of hydrogen. That doesn't mean that you have 4 pieces of hydrogen. So you don't have like hydrogen number 1, hydrogen number 2, hydrogen number 3, and hydrogen number 4. This one does not mean 4 of those. It literally means 4 of 6.022 times 10 to the power of 23 of these things, which is a lot. Okay, I don't even have a, like 1 million is already a really huge number, right? So if you have 1 million, that's how many zeros you have. This number goes beyond 1 million particles. This is huge, okay? Alright, so once you understand that, it's very simple. I remember when I first was learning chemistry back in the old days in high school, I was agonizing over what moles meant, but that's exactly what it is. Moles is just a grouping number. Alright, let's keep it very simple. So therefore, I'm going to reframe the problem. Here is an actual problem. If you have 4 moles worth of hydrogen, diatomic, and then you have 8 moles worth of oxygen, the question is, how many of these can you generate? And don't forget, moles are actual counting numbers. You're dealing with actual number of particles, not weights, actual number of particles. And because you're dealing with actual number of particles, you can use the recipe as it is. You don't need to change moles into anything else because moles are your actual counting pieces. But the problem is fundamentally the same as the first few problems we've gone over. So let's figure out which one runs out first. So if you have 4 moles worth of hydrogen, diatomic hydrogen, that's our given amount. The question is, how many moles of oxygen will we require? Same exact setup. So for every 2 moles, but now there are more words to write, unfortunately. See, before we just had like 1 letter, and now we have how many characters to write? These many characters. So for every 2 moles of hydrogen, according to the recipe, then you will require 1 of those. But again, 1 mole worth of oxygen. And then you sit there and you do the math. It's a very nice feeling of crossing these things out. Well, again, always cancel before, simplify before you multiply. It's 2 times 1. There it is. Maintaining the units in the numerator. So we have 2 moles worth of oxygen. What does that mean? That means that that's how many moles of oxygen we will need to use up all moles of hydrogen. Do we have enough? We have 8. We actually have 8 moles. We need only 2 moles. So yes, we have more than enough. So this is called the excess, as before. And then this one is called the limiting LR. So now that we've done this basic work, now we can do the main problem, which is to figure out how many moles of water. Well, you can kind of technically get it from here, right? Because it's a 2-to-1 ratio, gives you 2 moles. If it's a 2-to-1, you will also make 2. You will also get 2 moles of water. But here it is anyway, you know, just in case. So given that we have 4 moles of hydrogen, according to the recipe, right, it's going to be for every 2 moles of H2, you will make 1 mole of H2O. So calculating the numbers, cancel, 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 cancel. As stated before, we'll get exactly 2 moles worth of H2O. And that's it, 2 moles. Very simple, 2. Okay. But again, that's why I introduced pounds of bikes, because now we're going to be creeping ever so closer to actual chemistry problems. And here we finally arrived. If you have 10 grams worth of hydrogen, and then you have 64 grams worth of oxygen, the question is, how many grams worth of water can you generate? And again, this is going back to the bicycle pounds. You can't just say, oh, you know what, this is a 2-to-1 ratio, so therefore I can make 5 grams worth of water. You simply cannot do that because water molecules are not 5 grams. So what do we do? And the answer is you gotta reference the periodic table. So PT, short for periodic table. You actually need to look up the values in terms of moles. Everything you see on the periodic table is in reference to 1 mole. So I'm going to draw this crude diagram of a periodic table. So here it is. Gorgeous. And then we have hydrogen here. And then I think helium's right here. There's hydrogen. If you look up hydrogen on a periodic table, you will see some numbers, but the one that is important for our purposes is the one directly underneath this letter. It's going to be like 1.0079, I think. I think that they didn't put units. Okay, so you might see something like this. If you have a more detailed periodic table, you might see that this is going to be grams per moles. Maybe, maybe not. But let's assume that you have the simplest table given, which is something like this. And there's like a 1 here, right? What this means is basically this is per mole of a singular hydrogen atom. Wait, let me rephrase that. That's for a singular mole of only hydrogen. That's how many grams you will have for that one. And technically grams is not a weight unit, but you can think about it like a weight for now. So backtracking just a little bit, if you see this one, that's going to be grams. Grams per what? It's not explicitly stated, but it's going to be per mole. So here it is. So for every 1.0079 grams worth of hydrogen, singular hydrogen, you're going to have 1 mole of hydrogen. And that's it. For our purposes, I'm going to be simplifying the numbers because I like nice numbers. So rather than state that 1 mole is going to be 1.0079, I'm just going to simply say it's going to be 1 grams. You know, because my brain can only handle so many numbers. Sorry. So here are the magic numbers you are supposed to extract from the periodic table in order to actually do this problem, unless you've memorized the numbers. Which, if you have memorized them, what are you doing here, right? You have better things to be doing than learning chemistry that you already know. Alright. So, here are the magic numbers. For every 1 mole of hydrogen, that is essentially going to be 1 gram. 1 hydrogen only. So for every 1 representation, not diatomic, just 1 mole worth of oxygen, For our numbers, we're just going to call it 16 grams. Again, on the periodic table, you will get a higher degree of precision. You're going to get something like 15.999 or something like that. But for our purposes, let's keep it simple. Only 16 grams. Yes, 16 grams. So how do we use these ones to figure out this one, right? How many diatomic hydrogens do we actually have if we have 10 grams worth of diatomic hydrogens? Well, if you try to use this one with this one directly, you're going to get the wrong answer. So let me show you the wrong way first. And you will see why it's wrong if you write out the units. So it's going to be 10 grams worth of diatomic hydrogen. That's our given amount according to the periodic table, which you should always have at hand. You know, no one's going to deny it from you unless they are an absolutely terrible chemistry teacher. So if you just try to put 1 gram here and then you try to put 1 mole, it is wrong because this is for only one representation of hydrogen. It's only for monatomic hydrogen, not diatomic hydrogen. We are dealing with diatomics, not monatomic. Which, you know, because of that suffix, you kind of know where to go. So if we're not working with 1 hydrogen, because that's 1 atom, we need 2 hydrogens for this. 1, covalent bond it to the second one. And it's a very simple solution. All you need to do is put 2 here, easy, which means that you are dealing with 2 grams for 1 mole of diatomic hydrogen. We don't need to change this to 2 because for 1 diatomic hydrogen, that consists of hydrogen number 1 and then hydrogen number 2. The coefficient is 1. What are you dealing with? One of those is 1 grams, and then the other one is 1 grams for a given mole. So hence, it's going to be 1 times 2, which is here. I hope that's clear enough. Unfortunately, I don't get immediate feedback since there's literally no one here at the moment. But maybe I'll elaborate on a future stream. Maybe. But this is beside the point for now. Let's just obliterate that. Okay, so that's the actual conversion rate. So everything you get on the periodic table is raw. You need to make sure that it matches whatever you have right there. Again, diatomics, this is monatomic. You need to multiply this by 2 to get the actual conversion rate for 1 mole of diatomic hydrogen. Now that we have that, it's simple operations. Just cancel units with cancel units. Divide by 2, divide by 2, so you have 5 moles worth of hydrogen diatomic. 5 moles. There it is. Alright, and then of course we need to do the same thing for the oxygen. Let's move that up. So what do we got for the oxygen? So we are given a 64 grams worth of oxygen diatomic. Again, this is the wrong setup. If you just put 1 mole of singular oxygen type, it will be 16 grams for singular oxygen. But we don't have monatomic, we have diatomic oxygen. And then it's a very simple solution. We're concerned with diatomic oxygen. So this one also needs to be diatomic. So if 1 representation for 1 mole of oxygen is 16 grams, then we just need to covalent link it to another 16 grams. So that's 16 times 2 for the subscript, thereby giving us 32 grams. So this is the correct number, 32. Once you have that number down, straightforward maths, cancel, cancel, divide by 32, divide by 32. 2 moles worth of diatomic oxygen. So let's do a quick evaluation. What do we have so far? We have actual counting pieces of reactants. So we have 2 moles. We are given the 64 grams worth of oxygen means that we only have 2 moles of oxygen. And then the 10 grams worth of given amount of hydrogen means that we have 5 moles of hydrogen. Let's look at a recipe. Which one will run out first? Right? Which one runs out first? All we need to do is just do ratios. So I'm going to do arbitrarily select the hydrogen for further analysis. So if you build off of this, if you're lazy and you build it off of, and you put your work like right here, technically you're wrong because you're saying you're equating this one with this whole entire thing. But let's let's not be lazy. Let's start off a new line. So given that we figured out we have 5 moles worth of hydrogen, how many moles of oxygens will we require? So color or visual purposes. So it's going to be 2-to-1 ratio from our recipe. So the question is, how many moles of oxygen? Just cancel. We have 2.5. So thus 2.5 moles of oxygen. But what does that mean? That means that we require 2.5 moles of oxygen in order to use up 5 moles of H2. Do we have enough? No, we don't. We only have 2 moles worth of oxygen, and that's okay. Nothing to worry about. We haven't wasted our time by doing the work here, because we know that we don't have enough oxygen to use up all 5 moles of O2 because we require 2.5. We will base our production of water off of our limiting reactant, which we just figured out. That's limiting. So no need for that anymore at the moment. So eradicate that. We will base our entire answer of production off of our limiting reactant, which is right here. So continuing the good work, right? Moving on. So now we know we ain't working with the hydrogens, we're working with the oxygens. So 2 oxygens. Limiting reactant. According to our recipe, it's very simple. It's only 2 moles worth of oxygen will produce 1 mole worth of water. H2O. There it is. Cancel the units. Therefore, if the reaction goes to completion, then you will generate 2 moles worth of H2O. And that is our answer, right? And the answer is not that, unfortunately, because you have to go backwards just a little bit. This answer is in counting amount of water. You want to report your answer in grams, which is what people typically measure when they're in the laboratory. You don't measure counts, individual particles worth of water molecules. You just do it by bulk weight. Well, technically not weight, right? But, we'll just treat it as such. So we have the precursor to get to our answer, but this is not the answer we report because we need to report grams, the quote-unquote weights. So starting with the 2 moles of water produced. If we produce 2 moles worth of water, how many grams of water do we actually have? What do we do? What do we use to figure that out? And we already have the information right here. But that's not water, right? So what do we need in order to assemble a water in order to assemble an individual water molecule? You need 1 hydrogen here, you need 1 hydrogen, and then you need 1 oxygen connected. So remember, this is only count 1. This is only count 1 mole. This is count 2. So this hydrogen representation is 1 gram right there for 1 mole, and then 1 gram right there, and then this one is the oxygen, which is 16 grams. So if you summate all that, that's essentially a clean 18 grams because I made a nice number. So thus we can say for every 1 mole of water, that will get you 18 grams worth of water. We just figured it out by deriving it from the periodic table. And now we can just do the math. So cancel the moles, so it's going to be 2 times 18, which gives us a clean 36 grams worth of water. And that's the final answer to report. So there it is, 36 grams, right? And that's mechanically what we need to do. As a little bit of a side note, you might notice that, wait a minute, this is 10 grams, this is 64 grams. How do we end up with 36 grams? Like where does, or maybe you didn't have this question, I don't know. There's no chat to respond, unfortunately. But let's elaborate on that later on. But for now, this answer is good enough. Okay. Let's do some more. Let's do another problem with less verbiage, right? So this is going to be problem number 2, 2A. We're going to start off. Let me try to see if I can type again. Because writing it out is a real pain. Let me write test. Yeah. I don't know how this functions. You know what? Let me use it. Oh, actually, it's right there. I see how it works. Okay, that's very clunky. Okay, let me edit. Yeah, this is gonna be a real pain. It's gotta be you know what? I'm just gonna have to write it manually. That's okay. Okay, so basically we're gonna do a reaction. We're gonna have let me think. All right, here we go. Basically, we're going to have 18 grams worth of water. Given that we have 18 grams of water, and we're going to have 320 grams worth of water. Wait, why are we starting with water, right? Given that we have 18 grams worth of hydrogen, and we have 320 grams worth of oxygen, the question is, how many grams of water can we generate? And since this is kind of bothering me, let me just add a few things. Don't worry about what it means again, but just understand these are like formalities. This is actually, I'm going to put it as gas. This is a gas. That's a liquid. Okay, but don't worry about it. Going back to the problem. Again, we have 18 grams of hydrogen and we have 32 grams of oxygen. The question is, how many grams of H2O? How many grams of water? All right. Simple enough, right? So what are we given? What are we trying to do? Basically, we have information number 1 and information number 2. They are both on the reactant side. So that has to do with this and this. So of course, there's only one thing we don't know. What is that at the moment? So how many grams of water will be produced? So we definitely have enough information. We just now need to further evaluate what we actually have. We have grams. Remember, that's not actual counting pieces. So in order to use this recipe, you need to work with actual counting pieces and not grams. The short explanation of that is different atoms have different masses. So one oxygen, for example, is not equivalent to one hydrogen. Yeah, that's pretty much the small explanation. Okay. We need actual counting pieces, so thus we need to reference the periodic table yet again, but I'm going to give the crude numbers. So for every 1 mole for every 1 mole of just hydrogen, not diatomic, it's going to be 1 grams for now. And then for oxygen, for every 1 mole of singular oxygen, it's going to be 16 grams as approximate. So again, these ones you get straight from the periodic table. We have this. So our first job is to convert that. So given that we have 18 grams of H2, how many moles of H2 do we actually have? So we're trying to get moles of H2. Not H1, but H2. So we need to take this number, this 1 gram, which is only for 1 representation of hydrogen, and we need to multiply it by 2. So 2 grams. Cancel, cancel, cancel. 9 moles. How many? So that's just figuring out how many pieces of hydrogen we have. So the other question is, how many pieces of oxygen do we have? Same procedure. We have this one. Given that we have 320 grams worth of oxygen, diatomic, the conversion rate is for every 1 mole of diatomic oxygen, it's going to be 16 grams times 2 to make it diatomic. So 32. And make sure you cancel things. Cancel, cancel. I picked 320 because it's a very nice number, of course. It's only 10. So thus we can say we have 10 moles worth of oxygen. So 10 moles O2. Alright, so that is just getting us to the counting pieces. We have 9 moles of diatomic oxygen, hydrogen, and then we have 10 moles of diatomic oxygen. Diatomic hydrogen there. So the question is how many moles, or actually how many grams, right? But the intermediate question is how many moles of water do we actually generate? So what do we have? We have 9 moles of hydrogen, and then we have 10 moles of oxygen. Those are counting pieces again. We can now use the recipe right here. It's a 2-to-1 ratio, so visually you could kind of, or intuitively, you could kind of see that 9 is kind of lacking for 10, because for every one of these you require 2. So in order to use up all 10 moles of oxygen, you actually need 20 moles without doing the setup, right? So this one is not the, that's not the limiting reactant. I'm sorry, I'm speaking backwards. That is the limiting reactant because we don't have enough. We just, let me rephrase that. In order to use 10 moles of oxygen, we need 20 moles of hydrogen. We only have 9, which is insufficient. So therefore, this is the limiting. This one, we won't use it for now. So that's a lot of work. Let's clear the clutter because nobody wants to see all that. So given now that we know that the hydrogen is the limiting reactant, we're going to use it to figure out that one. So for every 9 moles of hydrogen we will be using, I'm sorry, that's how many we actually have. So for every 2 moles of hydrogen we're actually using, we're going to generate 1 mole of H2O. What does that, how many water molecules, how many moles of water molecules will we generate? It'll be 4.5, because 9 divided by 2. Again, we're not looking for moles as the answer, we're looking for grams. Always read the problem. It's always a tragedy when people have the right numbers, but then they report the wrong answer because of units. It's not technically what the problem's asking for. So this one will be a bridge to our answer of grams, 4.5 moles. So starting from 5 moles of water being generated, how many grams of water is that? So if we borrow the answer from our previous problem, it's going to be 1 moles is going to be 16, 1 oxygen, 2 hydrogens. So that's 2 plus 16, which is 18 grams. So again, this is just straight from the periodic table derivation. This one is our answer in terms of how many water molecules, how many moles of water molecules we have. But we want grams as a final answer. So just multiply those ones, and unfortunately my math begins to fail. Well, actually, no, it's okay. So we have 4 18s, which is going to be 72, and then we have half of 18, which is 9. So that's 81 grams worth of water. And that's the final answer we will report. Grams of water, grams of water. Yes. It is a done deal. At this point, I'll ask if anyone has any questions, but nobody's here. All right. And then we're just going to see how many problems I'm going to do before I get tired, before my voice starts to give out. But, you know, since I don't speak in a super enthusiastic voice, I could maybe do this for a while. I don't know my limit yet. Chemistry endurance problems in the future, maybe. Like I'm going to be doing 8 hours worth of chemistry. Or 8 hours worth of calculus. Or 8 hours worth of, I don't know, something else, right? But for now, let's stick with chemistry, because chemistry is easier to delineate. Its topics are easier to separate, and I feel it's just better to start with chemistry, maybe. Maybe. All right, let's do a different problem. At this point, I think I keep going back to trying to type, but that's a losing battle. So here is the problem. So the question is going to be 38 grams of water. I'm sorry, 8 grams of hydrogen. Reacts to completion. It's so slow. 8 grams of hydrogen reacts to completion with how many? 56. Yeah, 560 grams of oxygen. How many grams of water is generated? So this won't be complete English for sake of efficiency. So this is going to be the main question, and then there's going to be this question: how many grams of H2O generated? And here are some more questions, right? So this is problem 3. This is part A. Typically, you have like multiple multi-part problems. So that's part A. This is going to be part B. How many reactants, how many grams of reactants will be left over? Now you see there's going to be use for the other excess reactant. But, you know, we'll take it one step at a time. How many grams of reactant left over? And that's a pretty typical problem. So just 2 parts. We have part A and then we have part B. The part A one is the one we're already familiar with. Part B is the one we haven't really talked about. But the steps will be pretty much the same thing. You just need to frame your perspective. You need to understand what you're looking at. So for the first question, how many grams of H2O will be generated? You are using those ones as ingredients to figure out how many you have for that. We've already been doing that. For part B, how many grams of reactant will be left over? And let me complete it. How many grams of reactant remain? Yeah, that's better. Clean up. Okay. How many grams of reactant remain? That one is basically, one of these will be excessive, right? So it's either the hydrogen that's excess or it's the oxygen that's excess. And some of the reaction, one of these will be completely consumed, and then the other one will be, there'll be leftovers. That's why we call it excess again. So once we have the leftovers, we're going to use that leftovers to figure out how many grams remain. But I guess it's easier shown than said. So let's just do part A, because that's the standard one we've been doing. How many grams of H2O will be generated? Well, what are we given? So we have 2 grams worth of hydrogen. There it is. That's the recipe. And then we have 560 grams worth of oxygen. That's this other part. So the information we've been given is biased towards the left-hand side of this recipe. So what do we have? We have grams. So you need to convert them into counting pieces. So 8 grams hydrogen diatomic. Periodic table information, here it is again. We have going to be for every 1 mole of hydrogen, 1 gram approximate for 1 mole of singular oxygen, 16 gram approximate. So when you're trying to figure out diatomic right here, times 2. So 2 grams for 1 mole of hydrogen. How did I know it's diatomic? Unfortunately, you just got to memorize it. When you read the word in a word problem, you see the word hydrogen. And hydrogen, when you're dealing with hydrogen in chemistry, for the most part, like pretty much 99% of your cases, it's going to be diatomic. Because in nature, hydrogen by itself is very unstable. In order to achieve stability, it has to be linked with something else, typically. So that's the short answer, which you may or may not understand. But there it is, right? It's diatomic. Why? Because I told you. But I told you because it is unstable. So when you work with word problems, you assume that these molecules are stable. So you have to have diatomic hydrogen rather than singular atom hydrogen. All right, so do the maths. So cancel, cancel. You're left with 4. You actually have 4 moles worth of H2. So that takes care of this part. And then we have the other one to convert. We have 560 grams worth of oxygen, diatomic. Memorization. So how many grams? We have 16 grams for 1 mole. We want 2 because it's diatomic. So 16 times 2 is again 32 grams for 1 mole. So doing the simple mathematics, it's going to be, oh my goodness, I screwed up the numbers. It's supposed to be easy, but my brain for some reason can't do it. 50. So I'm going to cheat by using a calculator, even though I picked these numbers myself. Oh, that's why it's a kind of an awkward 17.5. Whoops. That's okay. Cancel, cancel. So what do we have? Evaluate. Take a moment to step back and look at what you have. This is how many counting pieces you have of hydrogen, how many counting pieces you have of oxygen. So which one is the limiting? Let's arbitrarily pick the 4. If we have 4, since we have 4 moles worth of hydrogen, how many moles of oxygen will we require to use up all 4 moles? Go to your recipe. It's going to be 2 of those to use one of those. So we'll cancel, cancel. That means that you need 2 moles worth of oxygen, and we have more than 2 moles worth of oxygen. So this one is excessive amount of oxygen. So thus, when you are using your recipe to figure out how many water molecules how many moles of water you will generate, we will be using the hydrogen, this one, limiting. This one is excess. So for part A, we're going to be disregarding this one, but just understand that since this is how many we have, this is how many we're going to use. We're going to subtract that from there to figure out how many we have left over. But that's for later. For now, we're rolling with the 4 moles of hydrogen. So start off with 4 moles. So if we have 4 moles, since we know we're going to use up all 4 moles of hydrogen, according to recipe 2 to 1. There's the hydrogen, and then it's going to generate 1 mole of H2O. Let me color pick the color pick. There you go. Cancel, cancel, which means that we're going to cancel this one more. So which means we're going to get 2 moles worth of H2O. But again, this is counting numbers we need to report our answers in grams. So this one gets funneled into our conversion rate right here. So for every, this is our generated amount. What's our conversion rate for every 1 mole in the denominator, 1 mole of H2O? That's pretty much 16 plus 1 plus 1, which is 18 grams. Again, derive that from the periodic table. Cancel those, cancel those. We have 2 times 18, which is going to be a clean 36 grams worth of water. So we are done with part A, 36 grams. Again, we're kind of ignoring sig figs, but that's not the point of this stream. So we have this. Yes. You know, that's more of the same thing. But the question of part B still remains. How many grams of reactant remain? Right? So it's very important you pay attention to what's being asked and where do you reference to find your answer. So we don't need this anymore. That's for part A. We're going back to this part. So let's cross that out, or let's delete that. This is part B. We are recycling our work for some slight efficiency. Okay. So if you recall, right, when we're trying to figure out which one's the limiting reactant and which one's the excess reactant, here's the work for determining how, if we wish to use up all 4 moles of hydrogen, how many moles of oxygen will we require? So if you do the math here, we require 2 moles worth of oxygen, diatomic. This is what we actually have. This is what we need, which we figured out using the ratio on the other ingredient. All right. So since that is excess, I'm going to put it in parenthetical. This is what we actually have. What we have in total. And then we have 2, this is what we need. So all you need to do is subtract what you need from what you have in total. So if we subtract the 2 moles that we need to use up all the limiting reactant, then we have the leftover moles of oxygen. So 17 minus 2 is 15. 15.5 moles of oxygen left over. And this one is what we need. Is it our answer? It is not our answer. So make sure you convert this. So working off of the 15.5 moles. How many grams do we actually have? Again, reference the periodic table. But since I gave the numbers, the crude approximations, here it is. It's going to be 1 mole is 16 grams. So for 16 grams of oxygen, it's 1 mole's oxygen, right? And that's wrong, because again, it's diatomic, it's 2. So make sure you clarify that always. So it's going to be 16 times 2, which is 32. For every 1 mole of diatomic oxygen. So when you do this one, unfortunately, the number is really gross. This is close to 16. So that's about half. Oh, what did I do? You notice I accidentally put the moles on top. So if you do the setup like this, this leads to moles squared, and then this one leads to grams. So what does it mean to have moles squared over grams? So for our purposes, that's useless. So I orientated this in the wrong fashion. So let's take this, put it on the bottom, on the top. Okay, and now everything looks good. There you go. All right, so we have a 15 times a 32, which is too much for my brain. I can only do single digits times 2 digits. So 15.5 times 32 gives us, oh, very clean, 496. 496 grams worth of oxygen. Again, what does this mean? That means that this is the leftover. This is the excessive amount based off of the moles of oxygen left over. So this is our leftover reactant. Okay, and that's pretty much concludes it for part B. So 2 answers. We have how many grams of water is generated, and then we have how many grams of leftover reactant remains, which is the oxygen. Okay, and I think I'm going to end the stream because I'm getting tired. I guess my voice is weaker than I thought. I haven't decided what's going to be the next topic. Maybe more of this. Maybe we'll do like a short marathon worth of stoichiometry problems. But for now, I'm going to call it. What else is there? That's pretty much it. So we'll move on to the end card. There it is. Until next time, I will see you. Have a good one. And hopefully there will be another stream in a reasonable amount of time. All right. Have a good one.